Hello and welcome to this new video. In this video, I'm going to finish chapter 4 with Taylor's formulas. There are 3 forms of Taylor's formula, but before stating them, let me just introduce some terminology. What do I mean by a function of class C1? A function f is of class C1 if it has a continuous derivative. And more generally, a function f is of class Cn if it has continuous derivatives up to order n and including order n. And f is of class C infinity if it has derivatives of all orders and they are necessarily continuous because a differentiable function is continuous. Now, we use sometimes the adjective smooth. Okay. Now, the concept of a smooth function is a little bit vague because it depends on the context. But usually, it means that the function has enough derivatives to make the discussion make sense. Okay, so for example, in differential geometry, a smooth function is usually C infinity. In complex variables, for example, when we talk about smooth paths, we mean paths of class C1. Okay? And it should be clear from the context what do we mean by that. Okay. So now, having said this, we can say that in general, Taylor's formulas actually they do the same thing. They provide an approximation of a smooth function by polynomials. Now, why there are 3 formulas? Because there are 3 different assumptions about the function f. 3 different assumptions on smoothness. Okay, so we have Taylor-Cauchy or Taylor with integral remainder. We have Taylor-Lagrange, and we have Taylor-Young. Okay, there is something common to all these, which is the approximation of a smooth function with polynomials. Now, the difference is in the form of the remainder. Okay. Now, but before I state them, let me just also introduce another terminology, the big O and small o notation, okay, which is very important actually. So, given a function defined on an interval I of r, taking positive or non-negative values, and a point in I or in plus infinity, and let f be another function. We write that f of x is a small o of g of x as x tends to a if the limit of the ratio is equal to 0. Or otherwise stated, f of x can be made less than epsilon g of x for every epsilon, provided x is sufficiently close to a. Okay, and we have the big O notation, which means, what do we mean by when you say that f is a big O of g? It means that the ratio of f over g is bounded by a certain constant in a neighborhood of a. Okay, so everything happens locally around a. A could be plus infinity. Okay, so now we shall give examples actually. And these notations are actually very important in computer science, as we shall see. So, for example, len of 1 plus x is a big O of x. Why? Well, you probably know that len of 1 plus x can be written as x minus x squared over 2 plus so on. If you don't know that, it's not a big deal. We shall prove it. It's easy. So locally, so len of 1 plus x divided by x actually is 1 plus something. So it's bounded near 0. Okay. You probably know that len of 1 plus x over x tends to 1, right? So it means that the ratio is bounded locally near 0. So it's less than a constant times x. Actually, it's just less than x for x positive. Sine x can be written as x plus big O of x cubed. Why? Because we can write sine of x as x plus x cubed over 6 or sorry, x minus x cubed over 6 plus so on. And so these higher terms are denoted by big O of x cubed. So it's less than a constant times x cubed. Okay, if it's the first time you encounter this formula, it's not a big deal because we can prove them easily by using Taylor's formulas or using just limits. Okay, and near infinity, ln of x is a small o of x. Why? Because ln of x over x tends to 0, as you know, and x tends to infinity. Okay, so in principle, these are known facts. And we shall encounter other examples actually in the exercises. Okay, and now in computer science, the big O notation especially is very important. Okay, because in computer science we study algorithms for solving certain problems. Okay, like sorting an array of size n or solving an n by n linear system. And we need to estimate the number of operations in the algorithm when the input size n of the problem is large. So this is what we call an asymptotic analysis. Okay, and all estimates for the complexity of the algorithm. Okay, so when the input size of the problem is big, how many operations we need in the worst case, of course. For example, the usual algorithm for multiplication of two n by n matrices, if you count the number of operations, it's not difficult to find exactly that they are 2n cubed minus n squared. Okay, you can just count how many additions and how many multiplications do we have. And now this 2n cubed minus n squared is precisely big O of n cubed. It's of the order big O of n cubes because this term is negligible when n is large. Okay, now there are better algorithms. This is the usual algorithm that you learn in linear algebra. But there is another algorithm called the Strassen algorithm, which requires much less operations, which require big O of n to the power 2.8074. This is really a significant advance, actually, because when n is large, okay, this is a significant amount of time saving when you pass from a big O of n cubed to big O of n to the power 2.8. Okay. Now, if you learn the selection sort for sorting an array, this requires a big O of n squared operation in the worst case. But there are quicker or more efficient algorithms. For example, the merge sort algorithm or the quick sort algorithms also require a big O of n log n. There is a significant amount because actually n squared over n log n tends to infinity. So there's really a significant advance. When n is big, the merge sort and the quick sort algorithms are much more efficient than the selection sort. Okay, so when we economize on time, so we may see the difference actually. And if you take a course on computer algorithms, actually, you may just do some experiments to see the difference. So maybe if this takes 1 minute, then this would take, for example, 1 second for n when n is large. Okay, and this is very important. So the time complexity of the algorithm is something very important, especially these days, because when you deal with big data, we need to really know how long does it take to solve a problem. Okay, and for example, there are even worse problems. For example, certain algorithms require what we call an exponential time. So it's a big O of 2 to the n, or a factorial time, like the algorithm for solving the traveling salesman problem. So these are hard problems, actually. And the known algorithms require a long time, so many operations that for when n is, for example, of order 100, so this may require centuries of computations. Okay, try to compute a factorial of 100. Okay, this is really above the capacities of most computers. So this is really an issue in computer science, the time complexity. And there's also another complexity, actually, which is important, which is the space complexity, which computes or estimate the space needed, the memory needed by the algorithm, which is another issue, actually. But time complexity is a more important issue, actually, because some algorithm may take centuries to be done if we follow certain known algorithms. Okay, anyway, so now let us go back to our Taylor's approximations. So we have, I will state them first without the proof, and then I will prove them. So Taylor-Cauchy, or Taylor with integral remainder, states what? So we have now a function of class Cn plus 1. So it has n plus 1 continuous derivatives. And we have, if you consider 2 points x and a in the interval, then we can write f of x as a polynomial of order n in x plus a remainder. And the remainder has a formula. It's 1 over n factorial times this integral. Okay? So the remainder is just the difference between. So this is what we call the Taylor polynomial of order n. We can denote it by Tn of x or Pn of x. Okay, so there's the common thing between all Taylor's formula is that we can write the function f as a polynomial plus a remainder. Okay, so this is the first form, or Taylor's Cauchy. Now Taylor-Lagrange, the assumptions on f are a little bit weaker. So instead of requiring a continuous n plus 1 derivative, we're just requiring the existence of the n plus 1 derivative. Okay, so here the fn plus 1 should be continuous. Here fn plus 1 should just exist. And then we have something similar. F of x is a Taylor polynomial, the same one, plus a remainder. But the remainder has a little bit slightly different form. It's fn plus 1 at some point c divided by n plus 1 factorial for some c between a and x. Okay, so they are very close together, but the difference is that in the assumption and in the form of the remainder. Okay, and lastly, Taylor-Young, it's the weakest form actually, because the assumption is just f to have derivative up to order n, and we just require that fn plus 1 exists at a. Okay, so this is just differentiability of fn at a. So it's the weakest assumption actually possible. And then we obtain something similar. So f of x can be written as a polynomial of order n, right, in x, plus a remainder. And I can write the remainder as x minus a to the n times a function tending to 0. So we may write, if you like, x minus a to the n times epsilon of x, where epsilon of x tends to 0. Right? So, and if you want to use the small o notation, we can write f of x as a polynomial plus a small o of x minus a to the n. Okay? So these are the three forms. They really look alike. They just differ by their assumptions on f and by the form of the remainder. Okay, so it depends what you want to do. Okay, now let us prove Taylor-Cauchy. It's very easy because you just use induction. Okay, for n equals 0, it's possible that to take n equals 0. It's not a problem, because when n equals 0, this is just f of a. Okay, so it means that we are approximating f of x by a constant plus a remainder. Okay, so now the remainder in this case is just 1 over 0 factorial, which is by convention 1, times the derivative of, so n equals 0, so this is just f prime, and this is just 1 because it's x minus t to the 0. So for n equals 0, the statement is correct because this is just the fundamental theorem of calculus, just saying that f of the integral from a to x of f prime is just f of x minus f of a. Okay, so now suppose that the formula holds for some n, and let us prove it for n plus 1, but provided that now f is of class Cn plus 1. So it's very easy. I take the remainder and integrate it by parts. Okay, so just first to make things clear, so just multiply by n factorial just to simplify the notation, and integrate this integral by parts. So we need to differentiate fn plus 1 to get fn plus 2, and we need to integrate x minus t to the n with respect to t, because here in this reasoning a and x are fixed. Now an antiderivative of x minus t to the n is minus x minus t to the power n plus 1 over n plus 1. So when we integrate by parts, we get this. This is the antiderivative of x minus t to the n, fn plus 1 evaluated between a and x, minus minus, because there are two minuses here. The derivative of fn plus 1 is fn plus 2, and times the antiderivative itself. But there are two minus cancelled, okay? And that's it. Now, if I evaluate this term, when t equal x, this is 0, and when t equal a, this is x minus a. So this is just x minus a to the n plus 1 over n plus 1 times fn plus 1 at a, and I don't touch this one. And now I divide by n factorial. So when I divide by n factorial, I get here n plus 1 times n factorial, so n plus 1 factorial. And here I get 1 over n plus 1 times n factorial, which is n plus 1 factorial. Okay? So this is the remainder. And that's it. So if I replace the remainder by this value in the formula, okay, so I just have to add, so this term plus this term is the remainder. So I get that f of x is now a polynomial of order n plus 1, of degree n plus 1, plus this remainder. And this is just the formula for n plus 1. Right? So it's very easy. Okay. Now, consequence. We can also write Taylor-Cauchy or Taylor integral remainder in this way. So just put instead of x a plus h. Okay, so h is the difference between x and a. So instead of x minus a, I have h. And now this can be, so this is the Taylor polynomial now as a function of h, which is the difference, plus a remainder. And there's a formula for this, is the integral formula for the remainder, and I just replaced x by a plus h. So this is the integral from a to x, and this is x minus t. So sometimes you may see Taylor-Cauchy or Taylor in this way, but these are completely equivalent actually. Okay. Now, what happens when h is small? Okay, this is where we usually use the formula when h is small. Okay, now this is, so the fn plus 1 is actually continuous, right? So in particular, it's bounded on any compact neighborhood of A. So on a neighborhood A minus delta, A plus delta, this is bounded by some constant n, m, let us say. And when we take absolute values, so the absolute value of the remainder is less than the integral of the absolute value, but I put actually absolute value again around the integral because h may be negative, right? So h could be positive or negative. So this is why, so this means that this is the integral from a to a plus h if h is positive, and the integral from a plus h to a if h is negative. Okay? And that's it. So now, if h is positive, I can get rid of the absolute value, and I get just a plus h minus t to the n, and I can integrate that. This is a plus h minus t to the n plus 1 over n plus 1 with a minus sign. So it's 0 at a plus h, and it's just h to the n plus 1 when t equal a, right? So we can evaluate this, and this gives me just absolute h to the power n plus 1. And this is actually, it's convenient to write this as a big O. Instead of writing a big O of modulus of h to the n plus 1, we just write big O of hn plus 1. So just to simplify the notation. But we really mean here big O of absolute value of h to the power n plus 1. So when h is small, the remainder is the big O of hn plus 1. Right? So now we can write Taylor's Cauchy in this way. So f of a plus h is, when h is small, is a polynomial of order of degree n in h plus terms of order hn plus 1. Okay? So this is a very good approximation actually when h is small. Okay? So even if we take when n equal 2 or 3, if n equal 2, this is just h cubed. So if h, let us say, is of order 0.01, this would be 10 to the minus 6 actually. So it's very small. The error or the remainder is very small when h is small. Okay. And this is really fundamental in numerical analysis when you want to do error estimates. And we shall see some examples in the exercises. Okay. Now, second for Taylor-Lagrange, as we did. Sorry here, so I just replaced, was an error here. It's just not Cn plus 1, it's Cn and Fn plus 1 exists. Okay, just an error. And the remainder is now of the form Fn plus 1 Fc divided by n plus 1 factorial. Okay, this is slightly more complicated to prove. So we introduced a new function, an auxiliary function, capital F of t, given by f of x minus the Taylor's polynomial, but not evaluated at x, at t, at a. It evaluates at any t. So you may take a variable here if you like. So for any t varies between a and x, or between x and a, same thing. When t equal a, we just exactly get Taylor's polynomial at a. Okay, so f of a is just the remainder. Okay, and my target is to prove that the remainder, or just f of a, is precisely of this form. Okay. Now, also observe that when you put t equal x, this is 0, because this is f of x minus f of x, and then x minus x, x minus x, x minus x. So f of x is also 0. We shall use this later. Now, we have a simplification here. If we take the kth term here, so, and differentiate it, this is a product actually as a function of t. When we differentiate this product, we get what? The k factorial doesn't change, so we differentiate fk one time and we don't change that, plus the derivative of x minus t to the k with respect to t times fkt. Now, when we differentiate x minus t to the k, we get k x minus t k minus 1 times minus 1. Okay, so the k divided by k factorial will become k minus 1 factorial. Okay, now we just do, we differentiate. So this, when you differentiate with respect to t, this is just 0. I get minus f prime. And here I get 2 terms. And here I get 2 terms, and so on. If you write these just one above the other, you will see that we get simplification, because this term cancels with the one before. This minus cancels with the one before. For example, here we get minus f prime of t, and when you differentiate with respect, there is a term which is f prime of t, so we get the cancellation between f prime and f prime. And the f double prime will cancel with this f double prime, and so on. So if you you write them properly, one above the other, you will convince yourself that when I differentiate all this sum, I just get one term, which is minus fn plus 1 of t divided by n factorial x minus t to the n. Okay, if you don't believe me, just do the computations. Okay, so write this term differentiated, then this term differentiated, then this term differentiated, and so on. And cancel, do the cancellation, and just get one term actually, which is the last one. Okay. Now, finally, we introduce another auxiliary function, which is that I call g of t, which is f of t minus x minus t over x minus a to the n plus 1 times f of a. Okay, this is the last change of variables that I do. And now what happens? If when you put t equal a, what happens? I get f of a, x minus a over x minus a, which is 1. So I get f of a minus f of a, which is 0. And when you put t equal x, this is x minus x, so it's 0, and I just get f of x. But we already observed that f of x is 0. So what do we have now? We have g of a is 0 and g of x is 0. Therefore, and g is differentiable actually, right? So the Rolle's theorem tells me that g prime vanishes at some c. Yeah, and this is my c actually. Now, when you compute g prime of t, you get what? You get f prime of t. This is just a constant, and here you get n plus 1 x minus t to the n, but minus minus cancel. So you get f prime of t plus n plus 1 x minus t to the n over so on, and just replace t by c now. And so you get precisely that. So this should be 0. This sum should be 0. Okay, so now f prime of c, you replace f prime of c by its value that I obtained here. And the second one I don't touch. So the sum of these two terms should be 0. Right? Sorry, there's a slight error here. It is x minus c, not x minus t. This is a c. So I have a common factor here, x minus c to the n, x minus c to the n. So I can simplify, and I get what actually? I get that a value of f of a. So f of a is just actually x minus a n plus 1 times the derivative over n factorial times n plus 1. Because this is 0. Okay, so I get the value f of a from this formula. And f of a is just the remainder, and that's it. So not trivial. Okay, so this is c, not t. Okay, and the same remark holds here. I can, if I put x minus a equal h, I also get this formula. And if in addition fn plus 1 is bounded, now I need to assume that fn plus 1 is bounded on a neighborhood of a, because fn plus 1 is not continuous, not necessarily continuous. So if in addition fn plus 1 is bounded near a, then I can do the same estimate. This is absolute value of h. So I get the same remark. The remainder in Taylor-Lagrange is the big O of hn plus 1. Okay, provided the n plus 1 derivative is bounded. Okay, which was automatic in Taylor-Cauchy, but it's not automatic, so I have to assume it. Okay. So this is what we call an asymptotic relation. Okay, it's an asymptotic approximation of f by a polynomial. It's really something local actually here. Okay, and finally Taylor-Young. So the assumption are now that f has n minus 1 derivatives, and the derivative at a, the derivative of fn minus 1 at a exists, just existence. And so we can write f of x is a polynomial plus a small o of x minus a to the n. Okay, now the approach here is a little bit different. We just apply L'Hopital rule several times, n minus 1 times. Okay, so we must prove that the difference between f and this polynomial divided by x minus a to the n tends to 0. This is just the meaning, okay? Because what I wrote here in the numerator is just Rn, because Rn is just the difference between f and its Taylor approximation. Okay, now if you put x equal a, you get 0 over 0, right? And of course, you are in the assumptions of L'Hopital rule, because the denominator vanishes only at a. Okay, so all the assumptions are there. So we just differentiate another time. Now, if we differentiate another time, we get f prime of x minus. Now the f prime of a comes from here, not from here, because this is the constant. Okay, so I just differentiate each term. Okay, the derivative of the last term with respect to x is just fn of a, which is a constant now, divided by n minus 1 factorial over x minus a n minus 1. Okay, and I differentiate the denominator, I get this. And I still have something of the form 0 over 0, because when I put x equals 0, I get 0 in the denominator. So I continue this n minus 2 times. So in total, I apply L'Hopital rule n minus 1 times. Okay? So what do I get actually after n minus 1? At the n minus 1 step, I get the limit of fn minus 1 of x minus fn minus 1 of a. This is so this is the last term actually, and this is the one before, right? And I still also have something of the form. Now this is easy. I don't need to use L'Hopital rule anymore. Just rearrange. So split the term into two fractions. So fn minus 1 at x minus fn minus 1 at a divided by x minus a. The n factorial doesn't count. And here simplify by x minus a and just get fn at a. Okay, and now we are almost done. The limit of this guy, of this fraction here, is just fn at a, because this is just because fn at a is the derivative of fn minus 1. Okay, so I get fn of a minus fn of a, and this is 0, and that's it. Okay, I don't need more than existence of fn at a. I don't need continuity or something. Okay, so this is fn of a minus itself, and this is 0, and that's it. So this concludes, and we already observed that. So we can write Taylor-Young in this form: fa plus h equal fa plus etc. And the remainder is now small o of hn, and not big O of hn plus 1. Now, of course, a big O of hn plus 1 is a small o, but the converse is not true. Okay? So this concludes the video and the course, actually. The lectures we are now done. In the next video, I'm going to solve the exercises of chapter 4, and this will conclude the course. And I wish you good luck in your exams. So thank you for your attention, and see you next time.